Excellent. Really nice to be back here again with you. You will notice that there is a still boring but slightly different background behind me today. That's because I moved offices between our lecture yesterday and the one this morning. Right, so today we are going to carry on talking about dark energy and extended theories of gravity. So just as a reminder, yesterday we talked a lot about, the cosmological constant problem, about the kind of different ways that you can phrase that, how to do that calculation carefully. And we talked about kind of how to get kind of a scalar field theory or a modification of gravity that sort of mimics that behavior. And we talked about quintessence models, and we talked about self-acceleration, and we talked a lot about scalar fields because that's kind of the simple example I've chosen to use to illustrate all of the physics that we're going to talk about. So we're still talking about scalar fields examples today. And today we're going to focus a little bit more on how you can construct models that avoid experimental tests. So if you remember yesterday, we talked about the fact that laboratory tests and tests of gravity within the solar system work extremely well, right? They really, really confirm that as far as we've seen on those scales, gravity is excellently described by general relativity, and there's no evidence that we need new physics on those scales. And then, you know, if we were to extrapolate that all the way out to cosmological scales and say, well, GR is definitely the right theory of physics, then we get some of these problems that we've been talking about. So the question is, how can you add in modifications of gravity? In our case, the way we've been talking about, how can you add in a scalar field that does something interesting on cosmological scales without kind of immediately coming into conflict with these local tests? And that's sort of not an obvious thing to do, right? Because on the one hand, you want a significant modification on some scales, on the very largest scales. You want a scalar field that can change how the behavior of the universe evolves. That's definitely a non-trivial thing. And on the other hand, on kind of solar system and below scales, we want a scalar field that is essentially negligible, that doesn't show up at all. So that kind of maybe immediately hints to you at where we're going with this, is that one of the things that people do is they make the theories non-linear. So you don't, if the theory is just linear, we should get the same effect on, same sort of order of magnitude of effect on all scales. And then that's where we immediately run into problems. So maybe non-linearities are going to be the way to go. And we'll see how that comes in a little bit later. But to start with, I am just going to sketch for you how our scalar fields that we've been talking about give rise to fifth forces, which is going to be their sort of most problematic observational consequence. Okay, and we're going to see this in a couple of ways, just to start to see how the calculations work. And also, again, to come back to this point that there are always, with these kinds of theories, multiple different ways of thinking about the theory, and in particular you can think about it as a modification of gravity, or you can think about it as just adding in a slightly weird extra scalar field, and yet no matter how you do these calculations, what matters is the observables, and you should get the same observables whichever way you do the calculation. Okay, so let's start with something fairly simple. So this is coming back again to our Lagrangian for our scalar field. So we have a kinetic term for a scalar field. For the moment, I'm just giving it a mass term. And now what we have in these final two terms is I've given us now explicitly a matter fermion. So yes, so this is the kinetic term for our, this is the kinetic term, the mass term here for our fermion. And then we have a term which explicitly couples our scalar fields to the fermion. It looks like a scalar field dependent fermion mass term. Now, the connection to the theories that we've been talking about previously is well, I guess on one level is obvious. This is a scalar field that couples to matter. But previously we've been talking about scalar fields that couple universally to the Ricci scalar, or if we do our frame transformation, couple universally to matter through a rescaling of the metric. So if that's the theory we're talking about, you might look at this and wonder, for example, why isn't there a scalar field dependent term hiding in this contraction of the indices with a metric here? And the point is that our starting point is that theory after we've canonically normalized our fermion again. So that's important because what I'm going to want to do in a minute is sketch how the calculation goes for a quantum theory. So I definitely need a canonically normalized fermion here. And once you do that, you go from our universally coupled scalar to one that couples to fermions just through this kind of mass term. Okay. And as it said, we are going to ask what is the consequence of this kind of interaction? Well, the kind of most obvious tree level consequence is that we can draw this kind of Feynman diagram. So here, the solid lines are our fermions, and they are scattering off. We've got two fermions, and they're scattering off one another by exchange of a scalar field. Okay. And if we can compute this should tell us, at least one of the effects of our scalar field. So just to sketch that calculation for you, how that works to compute this Feynman diagram, we first of all need to know what our scalar propagator is for the exchange of our scalar field here. Okay, so there's some momentum q and some mass of our scalar fields. I've written the fermion propagator for completeness. Actually, we're not going to use this because all our fermions are on external legs. And then there's some contribution from the vertex, and we have two of those. Okay. So if we want to write down then, sorry, just need to scroll. If we want to write down the scattering amplitude, oh, hang on a second. I need to tell you, right, a couple more things. We want to write down the scattering amplitude for this diagram, okay, for our scalar exchange. We are going to write our external fermions just as U. And because of the kinds of experiments that we're interested in, if you think about when we talk about tests of gravity, we're talking about planetary motions, or we're talking about kind of the deflection of heavy source masses in the laboratory. None of those are relativistic experiments. This is all kind of very slow moving, very heavy, kind of heavy objects, heavy extended objects. So we're also going to take the non-relativistic limit of this calculation. And so putting those pieces together, let's just have our diagram back. Yeah, so if we remember what we really need, we've got 4 external fermions here, 2 vertices and a scalar propagator. And that gives us, we get a scattering amplitude that looks like this. So we've got our scalar propagator in the middle, our 4 external fermions, and 2 factors of G that are coming from our 2 vertices. And then what we're going to do is we're going to say, as I said, that we're going to take the non-relativistic limit. That means that this square of the difference in the 4 momenta becomes the square of the difference of the 3 momenta of our particles here to leading order. And because of the normalization that we've chosen, the contraction of our external fermions, the contraction of our external fermions is going to mean that we're just going to pick up factors of square root m. So I'm just sketching this for you for the moment because I think all I want really is sort of to give you a sense of where where the final answer comes from, rather than for us to get too hung up on factors of 2 and things like that. I hope that's okay. The full version of the calculation is laid out both in the lecture notes, and it's in many of the introductory quantum field theory textbooks, like, for example, Peskin and Schroeder. So if we follow this through, we make our non-relativistic approximation. What we get for the scattering amplitude at the end of the day is that this is, again, as I said, to leading order, that we get this expression. So we get 2 factors of m, so 1 from each of our contractions of the external legs. We get our g squared coming from our 2 interaction vertices, and then we get that we have the difference in the 3 momenta squared minus m phi squared. Okay, so that's our non-relativistic approximation to the scattering amplitude. Okay, but this is not yet a force. We're seeing kind of this as a scattering amplitude, but what is the real space version of this that shows up in an experiment, in the kinds of experiments that we use to search for fifth forces. And to do that, I think what we want to do is to think about, actually now, instead of 2 particles scattering off one another, which is what we've calculated here, to think of this as 1 particle now scattering off the potential sourced by the other. Okay, so we can move into a frame where what we're thinking of is one of our fermions sources a potential, sources a scalar field potential, and then the other fermion scatters off that. And in that case, so we can think of that then, again, because we've said we're thinking about this in the non-relativistic limit. So the non-relativistic scattering, this is just like a Schrodinger equation. So we're thinking now of something like this. So this is a Schrodinger equation. So we've got some V, some potential that we're scattering off. Okay. And again, thinking about thinking about the scattering picture that we've been talking about, we can compute a scattering amplitude in quantum mechanics from the Schrodinger equation in the way that I'm sure you're very used to doing at undergraduate level. And if we do that, yeah.
Okay, thank you. Is this frame that we've moved into the Jordan frame that we were talking about yesterday?
Yes, no, so we are now in the Einstein frame, actually. So we are assuming, well, at the moment I'm not talking about gravity at all. So I'm kind of assuming that in this situation, well, either gravity is negligible or we can compute the scattering amplitude of our scalar and then add it to the scattering amplitude, exchanging a graviton. But the theory that I've started with here is one where the coupling of the scalar field to matter is explicit. So that is an Einstein frame picture. So Einstein frame means that the gravitational action just looks like Einstein-Hilbert, and all the effects of the scalar field are in the matter sector, if you like. Whereas the Jordan frame, the matter sector looks standard. There's no additional scalar, but we have our extra field in the gravitational sector. Does that answer your question?
Yes, thank you.
No worries. Cool. So if we do the comparison between the scattering that we would compute with our Schrodinger equation and the scattering amplitude that we just calculated, and I'm skipping just a few steps here, we get that's the potential that our particles are scattering off looks like this. Okay, so that's it. That's the potential. So we're getting there, because we know that if we had a real space potential, then the gradient of that would give us the force due to the scalar field. So the only problem we have at this point is that we've still, because we've done this from a Feynman diagram calculation, we've got a Fourier transform of that potential, but that's okay. We can undo Fourier transforms. So we can invert this. And all which you can do by by integrating over Q, closing your contour in the complex plane. And what we get at the end of the day is that we get then real space potential, which looks like this. Okay. So this then is, and I realize this is really just a sketch. There are steps that I've skipped here that if you wanted to reproduce this, you would have to go back and fill in for yourselves. But this is then the statement that 2-to-2 particle scattering of this form, exchanging a scalar field, leads us to a real space potential of this form, okay, where the mass of our scalar field comes in this exponential term. We've got a 1/r dependence, as we would expect, and as we've said, a dependence on the square of the coupling constant. Now, so we can see that if the mass of our scalar field is very, very light, firstly, this then becomes a long range force, and also that it looks very much like the kinds of sorry, I've lost my train of thought there. It looks very much like a gravitational potential. Then we've got 1/r dependence and a coupling constant squared, and so it's going to mimic the effects of gravity on those scales in those experiments. Right. Okay. So this is the kind of, this is a Yukawa potential, and this is what we talked about last time. Actually, maybe let's just bring that slide back up, where we talked about all of these very good experimental constraints. So this is what we're going to have to modify if we want to be able to avoid these kinds of constraints. And as we've seen, the kind of the relevant pieces are the mass of our scalar fields and the strength of the coupling, which here I've called alpha times g, but previously we've just called little g squared. So what you could think about is, are there ways of maybe changing the mass of my scalar field to change the way that this that the scalar field is mediating the force? Maybe if I can arrange for the mass of the scalar field to change depending on the experiment that I'm doing, maybe then I get an exponential suppression in some situations and not in others. Or maybe I could arrange for some reason the coupling constant to be different in some environments compared to others. If it's smaller on kind of solar system and terrestrial scales, then maybe we can suppress the force. Sorry, is there a question? Or
yes, thank you.
Yes.
Yeah, so instead of introducing a new scalar field, if we were to start with introducing a new Majorana fermion, would we still get this 1/r potential?
I think the 1/r does just come from the fact essentially that you've got a 1/q squared in the propagator. Hang on, let me go back. Yeah, so
that's kind of what I was thinking.
Yeah. So I think the fact that you have a slightly different p dependence, if this were a fermion propagator here rather than a scalar one, would mean that you would get a different scaling of the force law. Yeah, I think that's right.
Okay, thank you.
Okay, so this is where we're going. We're going to sort of think about how do we end up modifying this so it's not so constrained? How can we do that? And this is going to be the key, and this is again the challenge for this kind of theory. How do we do it without fine-tuning the coupling constant? Because that would be the easy way to suppress our force in terrestrial experiments. It would just be to make our coupling really, really tiny. But then we stop the theory from being able to have kind of significant cosmological consequences. And similarly, the other way to suppress the effects of this scalar would be to make the mass really big, but again, that means that you struggle to have any impact on cosmological scales. Okay, so before we get into the details of doing that, though, let me just we're actually going to recover the same result in a different way. Again, very quickly, very schematically, just to see how that calculation goes and why even it. So what I've just shown you is very much the sort of particle physics way of thinking about this. Is I've added in a new scalar field, it interacts with my fermions, therefore I can write down all of the Feynman diagrams, I can write down this tree level exchange, and I get my scalar fifth force out at the end of the day. But if we're thinking about this as a modification of gravity, and as we talked about, as you just asked in your good question, if we think about this as a conformally coupled scalar where we have these two frames, how do I get the same result out of my calculation, thinking about this as a gravitational theory? So if you remember last time, we had these two pictures where we had two versions of the theory that we could write either in terms of a tilde metric or an untilde metric, and those metrics were related by some function a of our scalar field. Okay, and one of these, as we said, is the Einstein frame, where, if you like, gravity works as normal, it has an Einstein-Hilbert action, but our scalar field couples to matter. Or we can think about this as a Jordan frame description where matter works as normal and we have a scalar field in the gravity sector, so we have to be more careful about our gravitational calculations. So how in a gravitational theory do we compute what the forces are, what the gravitational forces are on individual particles? Well, that comes from the geodesic equation, which you may remember. And although these are positions of our test particles, and we're differentiating with respect to the parameterization of our world line lambda, and these are the Christoffel symbols corresponding to the metric. So if we were working in the picture corresponding to G tilde, this would be our geodesic equation. Okay. But what if we want to transform this into the picture in terms of the other metric? Well, that's fine. We can do that. Our metric shows up in these Christoffel symbols. So we have to calculate what these are in terms of now A and the untilde G. And you'll remember that Christoffel symbols involve calculating derivatives of the metric. So if we compute our Christoffel symbols now in terms of A and G, if we substitute our G tilde into here, we're going to get derivatives of A and derivatives of our scalar field showing up. And that's already kind of is all you need to know to see how the derivative of the scalar field is going to enter this calculation. Okay. So to make our lives a bit simpler, and we're going to do this for most of the rest of this lecture, I'm going to make two choices. I'm going to assume that I can Taylor expand my coupling function A, so that it's at leading order it's 1, and then we've just got some linear piece and some energy scale m here. And I'm also at this point going to assume that I can set my gravitational metric to be just a Minkowski metric. For the moment, that's just sort of for ease to show you kind of how the scalar field comes in here, to not have to repeat the standard gravitational calculation as well. But actually some of this in a lot of the situations we're going to be interested in, this is a reasonable approximation, and maybe our scalar field couples to matter a bit more strongly than gravity, and that's why we can include the effects of the scalar field whilst kind of still ignoring the gravitational correction. Okay, so what we've said is that we want this is our geodesic equation in terms of the tilted metric. We want to write it in terms of the untilted metric. So we're going to need some new fall velocity, some untilted fall velocity, which is x by d lambda. If we give that some index, which is normalized with respect to our untilted metric. Say that theta mu, oh, sorry, I want these downstairs, mu is equal to -1. And then we can write the acceleration defined in terms of that velocity as mu. Okay. So those are all of the pieces that we need. Okay, we have our equation, we substitute in our new, we substitute in this expression for the metric, and then we rewrite that expression in terms of the untilted fall velocity and acceleration. And the answer that we get at the end, again, we're assuming that things are non-relativistic. The answer that we get from that calculation, and again, I'm skipping a whole bunch of algebra here, is that this is okay. So we've got our scalar field showing up here, as we said. So this is a derivative with respect to the new spatial coordinate. We've got our scalar field showing up. In fact, I've said I've Taylor expanded our expression for the coupling function A. So actually, I should have already neglected this term in the denominator. And then I have here the fall velocity and our background space-time. And so it's not immediately looking like a force law that we recognize, but if we consider static, spherically symmetric situation, then we're going to set our fall velocity just to be things moving forwards in time and not moving in space. And then taking just the radial component, which is the only acceleration, which is non-zero, we find that this is, we get 1/m, and then we get d phi by dx mu. Sorry. Dear, I've mixed up my indices there. Hang on, let me write that again. We get a times r is -1/m d phi by dr. So that would be no surprise to us if we were talking about gravity, or if we were talking about electromagnetism, that we have an acceleration that is the derivative of something that looks like a potential. So that's the first thing then to realize here, I guess, is that our scalar field is acting like the potential for this force. Or in fact, sorry, just lost my page. Where have I put that? Never mind. Underneath. Because we've got a of phi, we've made this approximation here that it's just 1 + phi/m. In fact, if you were to do the calculation more generally, you would find out that it's actually a of phi that is actually acting as our potential. And we take the gradient of that, and we get a scalar force. So if we wanted to know what that force is, we need to compute phi. as a function of r in this way of doing the calculation, and then hopefully we recover the standard kind of the Yukawa version of the force law that we have just found from the Feynman diagram calculation as well. Okay. Any questions about that?
No surprise, I do have one actually. That's okay.
Yeah.
And I just lost it. Sorry, it just left my brain. I'll ask you.
Okay. Well, I'll pause again in a minute. So if it comes back to you.
There's actually a question on Zoom in the chat.
Yeah, thank you.
I'll read it for you.
I have, you're absolutely right. That's in the, I'm sorry, it says.
The question actually for the people here, the question is that the indices are confusing a bit. Should it be a mu?
Yeah, no, you're completely right. Because there's a mu contracted here, so there's a free index mu on the right hand side, so this should have been a mu, and I suspect that goes back to the previous calculation as well. I'm sorry for confusing that.
And I remember mine.
Okay.
That's okay, thanks. So in this approximation where we're saying A is basically equal to 1 and we neglect the linear term when we're calculating the acceleration, aren't we then saying that our scalar field isn't really modifying our metric in any way? So it just is like introducing a normal non-exotic scalar field.
Right. So yeah, if I come back to here, so I think so what you're asking is that I've kind of assumed here that this metric is not modified. I think is your question. So is that yeah. So I guess the first thing to say is when as always, when you make an assumption, you should do your calculation and then go back and check that that in fact that was that assumption holds with the final answer that you get, which you can do in these theories. Now, you could also completely do this calculation not making this assumption. What I could have written down the metric for Newtonian potential here. We could have kept that in the calculation, and then what we would have found at the end of the day is that we get one term that looks like the derivative of our scalar field, plus, again, assuming that we're in the weak gravity limit, plus the derivative of our Newtonian potential. I dropped that, I guess, to keep things a little bit tidier. But if you wanted to do that version of the calculation, that you can follow it through, and you just find that these two things add up. Now, of course, you should check at the end of the calculation that that this scalar field, first of all, doesn't mix with the Newtonian potential. Beyond that, that will give you some conditions on how big the gradients of your scalar field can be for that approximation to be true. So this certainly wouldn't hold, around a black hole or something like that. But for the sorts of experiments we're talking about in the solar system and in the lab, it's perfectly reasonable to say that we're working in a weak gravity regime. The other thing that you might worry about is, okay, but then I'm going to have, so if I actually say that instead, actually what I have is this minus the derivative of my Newtonian potential with respect to R. In doing this version of the calculation, what I would then do is go away and compute the Newtonian potential due to my massive source, and then I know how, and the scalar field potential due to my source by my massive source, and take the derivatives of those, add them together. That gives me my acceleration. But you might worry then that I'm forgetting the fact that I have some energy density stored in my scalar field, and maybe that should be sourcing the Newtonian potential as well. And again, you can check whether that is a significant contribution or not. And for something like if we're doing a Cavendish type experiment in the laboratory where we've just got two test masses, two large test masses and two small ones, and we're looking for the deflection of the small test masses towards the large ones, whoops, then that's completely negligible. But actually it isn't completely negligible in the solar system. That small amount of energy density in the scalar field does contribute enough to the Newtonian potential in the solar system that you would expect to see, for example, its effects on light bending, light being deflected by the sun. So those are some very precise, again, a really precise test of gravity that we can do in the solar system. And there you do have to be careful not to neglect the fact that the scalar field also sources its own gravitational potential, and you should include that as well if you're doing a test. It was a very long answer to your question. Did that actually answer your question, or have I gone off on a tangent?
Yes, no, I think it did. So basically our scalar field is still, I guess, modifying gravity. I don't know if that's the right language, but modifying gravity enough that it solves the cosmological constant problem. But on small scales, it's okay to make that assumption.
Ah, okay, right. So I did go off on a tangent and not answer your question. So for the moment, we are just talking about these scalar fields as a possible way to modify gravity. Right now, so I'm building up to how do we get to the point where we can have these scalar fields that maybe have large scale cosmological consequences, and we're going to get there. But for the moment, this is just a scalar field modification of gravity. And if this was all we had in terms of what I've just shown you, then this scalar field would be constrained by those experiments, and actually you would struggle to get a large scale cosmological consequence. So we're going to come on next basically to how we get this kind of nonlinear behavior where maybe you can solve cosmological problems as well. I'm sorry if that wasn't clear.
No, that's great. Thank you so much.
Okay, so we would like to know, okay, so just going to build up the standard version of the equation. There's one calculation, there's one final piece that we're missing before we start talking about nonlinear physics, which is that we want to know what our scalar field looks like around a source. And we're going to talk about, for the rest of this lecture, we're going to talk about spherically symmetric sources of some constant radius and r and constant density rho. Okay, now spheres are pretty good approximations to the planets and moons and stars in the solar system. So that's kind of a good baseline calculation for those kinds of constraints. It also gives us a lot of intuition for what happens in a laboratory test as well. Okay, so that's the kind of source we would like to put into our scalar equation. And just as a reminder, again, this is our Lagrangian for our scalar fields. I'm chopping and changing between the ways in which I'm writing this, and that's precisely because each kind of question you ask, or depending on the observable you want to compute, or the way in which you want to do the calculation, there's sort of a choice you can make for what is the easier point to start from. So here again, we've got our scalar field with a kinetic term, a mass term, and our matter Lagrangian now, our matter fields, and they're moving on this rescaled metric, which depends on our scalar field. Okay, so this is what we've just been talking about, and our geodesic equation calculation that we've just done says that the effects of the scalar field, the force due to the scalar, is the derivative of phi over m. Okay. Now, if you take this Lagrangian and vary it with respect to phi, you get an equation of motion that looks like this. Now, the first two terms are hopefully kind of obvious, that the variation of the kinetic term gives us a box phi. The variation of the mass term gives us an minus m squared phi. The form of this term here comes from the fact that our matter Lagrangian now depends on our scalar field. But it depends on the scalar field in the way, so where the scalar field is always coming in multiplying the metric. So we use the fact that the variation of the matter Lagrangian with respect to the metric is an energy momentum tensor. And then writing out the scalar field explicitly in that, we get that going from here to here, varying our Lagrangian with respect to phi brings us in an energy momentum tensor dependence. So this is how we get that our scalar field, our massive scalar field, is sourced by the energy momentum tensor of matter. And then at this point, we're gonna put in what we've just said, that we want our matter to be a spherically symmetric source of constant density, a static but spherically symmetric source of constant density. And all of that together brings us to this being the equation that we want to solve, okay? So it's spherically symmetric and static, so our Laplacian just becomes phi double prime plus 2 phi prime over r. The mass term for our scalar field is still there. Our coupling is still here. And then we say we've got some constant density rho inside the radius r and just zero density outside. Okay. And now this is an equation of motion that you can solve. We want to impose, and the way that you can do it, if you want to work through it, is you solve inside the source, where we do have this source density rho. You solve outside the source. So we solve inside and outside. We impose our boundary conditions that at the origin, the fields, the derivative of the field at the origin is 0, so that we don't get any nasty divergences. And also that phi goes to 0 at infinity. So there's no divergence at infinity either. And then that phi and phi prime are continuous at r. Okay, so that shouldn't need, there's no surprises there. Those are kind of the obvious boundary conditions that you would expect for a compact source sourcing a scalar field equation like this. And at the end of the day, if you do that, you work through the calculation again, we get that outside, so r greater than capital R outside our source, we get that phi is, we've got a coupling again, got the mass of our source over 8 pi, and that we get e to the minus m over r. Okay, so this is, in this version of the calculation, in the classical version of the calculation, how we recover again our Yukawa potential. So we've got our exponential suppression, and I have messed up the minus signs there, that should be a plus. We've got our exponential suppression of the mass at large r, we've got our 1 over r10, and then we've got the mass of our source coming in here. Okay. So this is our problematic Yukawa potential, if you like, and then the fifth force that it sources is just the derivative of phi, as we've just seen. And this is what we're going to want to modify. But I've sketched this version of the calculation because this is the calculation that we're going to now go back and see how we can alter. Okay. Right. And maybe we can see here, now we're thinking about it in terms of a differential equation. Again, we can see the kinds of things we can modify. And basically there's 3 types of terms here. And so you'll be unsurprised to hear that there are 3 types of ways that we can think about modifying this equation. There's a gradient term here or a kinetic term. We could think about modifying that. If we change the kinetic term, we certainly change how the scalar field responds to any kind of source. As we said, we can change the mass term. And what we're going to see in a minute is that we can think about making the mass of our scalar field large inside the source and small outside, which changes again the way the scalar field responds to the source, and changes how far you can transmit your scalar force. Or we can change the way that our scalar field is sourced on the right hand side. So maybe instead of this just being 1/m, maybe there's some scalar field dependence here, which again changes how things are sourced. Okay, so what I have now for the rest of this lecture is two examples of that, which we're just going to talk about how they work. Sorry?
Can I ask a question?
Yes, of course.
How should I interpret the big M, the capital M? It's like just a parameter of the expansion, or?
Yeah. So we said absolutely that it came from a coupling function, which we wrote as 1 plus phi over m. So you can just think about it as a parameter that characterizes this coupling. And if I kept higher order terms in this expansion, maybe I would need to include other scales in the problem as well. Not for the moment, I'm not doing that. But also, if we look at this final result here, you can see that it's the scale that controls the strength of this interaction. So actually, it's fair to think of this as actually the energy scale controlling the strength of the interaction with matter. So as the coupling constant of our theory, so the linear coupling constant of the theory.
Okay, thank you.
Okay, so the first version of how we're going to modify this that I'm going to talk to you about is known as a chameleon theory. And it's known as a chameleon, or the name arises because it's a scalar field that is supposed to change its behavior depending on the environment. Okay, so and in order to camouflage itself as well. So that's where the name comes from. And we have, again, a very similar Lagrangian to the one that we've been talking about. We've got a kinetic term here, but now we've chosen a different potential. So this is not just a mass term anymore. In fact, we've chosen an inverse power law potential. And then we still have our coupling to matter. And again, I've expanded our coupling function like this. And the first thing to say is that the reason for choosing this potential, first of all, is that it's a very common choice for quintessence theories. So if this is our v of phi, this is a function of phi. Our inverse power law, let me choose a different color, goes like this. And so the idea for using this kind of potential as a quintessence theory is that you start at some initial position somewhere on the steeper part of this potential, and then the field kind of during cosmological history will just roll down your potential at some point, and it just keeps rolling along the flat part. But at some point, because the universe is expanding and we have this Hubble friction term in the equation of motion for our scalar field, at some point it gets frozen. So the friction term dominates, the field gets stuck here, and then there's some height of the potential there, which becomes our effective cosmological constant at late times. So this is the sort of freezing quintessence scenario. And because the friction term takes over, we get that phi dot squared is much less than v of phi, which, as we talked about last time, was the condition that we needed to have a scalar field acting like a cosmological constant. So that's the reason that this potential was chosen, and it's a nice one to illustrate the mechanism here. So this is a theory that you might like to be a quintessence model. But I should say that what we're going to talk about is not like wedded to this choice of potential. There are other choices that we could have made almost anything other than a mass term will work for what we're about to talk about. Because what happens is, now if we write down the equation of motion for our scalar field, we know that we're going to get a box phi from the kinetic term. We're going to get a derivative of our potential, and as we saw previously, just to go back to that, we get a source term on the right hand side, which depends on our matter source. From the point of view of our scalar fields, you can think about those two terms, the bare potential that we've put in and the effect of the coupling to matter actually is acting together to be an effective potential. Let me show you what I mean by that. So the scalar field now behaves as if it's governed by this effective potential. This is what we've just seen, lambda, our inverse power law with some new scale lambda in it, and our coupling to matter sourced by the density. And, oh, sorry, excuse me. The combination of those two terms means that actually that the effective potential, the sum of the two, has a minimum. So there's a nice position now for the field to be stabilized in, which is good. Although, as we've seen, maybe even without that, the Hubble friction would stop the field from running away to infinity. But now the coupling to matter stops that. There's a nice minimum for the field to sit in. But the position of that minimum changes as you change the density, right? In low density environments, it's larger values of phi, and in high density environments where the gradient of this piece here increases, it's at smaller values of phi. And more importantly, the steepness of the potential around that minimum, which so the field is much more trapped in that minimum. The mass of fluctuations around that minimum is much larger, okay, in a high density environment than a low density environment. So this is, as we've talked about, this is one way that you can imagine getting some non-linearity into your theory that helps explain why you can have significant effects on cosmological scales, but negligible effects in the laboratory. Cosmology is, as we know, some of the lowest density environments we can think of. So the field is there comparatively light, but in the solar system and in the interior of planets or our test masses, the density is much higher. We get a smaller field value, a smaller vacuum expectation value, or sorry, a smaller expectation value for our scalar field, but also the mass of the field is much larger. It's much harder for the field to evolve. And what does that mean? Let me just think how I want to do this.
Can I ask a question?
Sure.
Thanks. So yesterday when we were talking about the free massive scalar, we found that rho goes like mass to the fourth. Is that the same here? So will the second term and that effective potential go like mass cubed?
Okay, I think we're confusing. So what I mean by rho here is the energy density of matter. So everything else, all of the other fields apart from my scalar field and the gravitational, the graviton. What we computed last time was the vacuum contribution of our scalar field to, sorry, the contribution of the vacuum fluctuations of our scalar field to the background energy density of the universe. So one is this rho that we're talking about here are our matter fields. What we talked about last time was a contribution to an energy density contribution from the scalar field itself. Is that distinction clear?
Yes, it is. That clears things up. Thank you.
Right. Okay. Okay, let me just, rather than do the calculation, because I do want to make sure I finish in time for if there are any questions at the end today. So let me just talk you through how this calculation goes rather than showing it to you, working through all the details. Oh dear, sorry. So let's, looking at this slide, this is our spherically symmetric source mass here. And we're going to think about how the scalar field behaves in and around that source mass. Now outside, we have some so let's just say what we're looking at on the right hand side there here. This is the sketch of the potential as a function of the scalar field that we've been talking about. The solid black line is our inverse power law potential. So that's the bare potential. If there were no matter in the universe, the field would just evolve and that potential would run down until eventually it freezes in at some point. Now, if we have some background energy density, the fields can't run all the way to infinity. In fact, it just gets stopped in some minimum here, where the mass of fluctuations around that minimum is relatively light. So if we wanted to solve for how our field is behaving outside the source, we'd solve for fluctuations around this minimum here. Okay, now if we think about the other extreme, if we think about deep inside the source, if our source is very heavy, much heavier than the background density, the field is now moving in the sum of the solid black line and the black dashed line. So the minimum of the field has shifted. The mass of fluctuations around that minimum is much larger. And in fact, it's really hard. It's much harder for the field to evolve. It costs more energy. It's more so there's a region in the interior of our object where the field is effectively constant and stuck at this value. But then we have to interpolate between those two regimes, right? Deep inside where the field is stuck here, and far away outside where the field wants to be very close to this background value. And the way the field, excuse me, the way that happens is that in a shell near the surface of our object, the field has to grow. And it grows still in this, it grows along with the potential dominated by this black dotted line. Okay, so that's kind of the three regimes of behavior we have. And we could solve for the evolution of this scalar field, or the spatial distribution of our scalar field, by solving for those three regions. So far outside, deep inside, and this shell region, just as in the way we did before when we had, when we were solving just for our massive scalar. We solved inside, we solved outside, we matched at the boundary. Now we have three regions. So we solve in the core, we solve in the shell, we solve outside, and then we match at those two boundaries, and we can compute the behavior of the fields. And what you find coming out of that is that the force, the scalar fifth force, is now not sourced by the whole of the mass of this object. In fact, it's only sourced by the matter that lives in a shell near the surface. And you can kind of see that, I think, here by saying that the forces arrive because we can build up gradients in the potential. But what we're saying here is it's deep inside the core of our object. Actually, the field can't move. We can't get a deeper and deeper potential because the field just gets trapped here. So there's a limit to how deep the potential can be, if you like. Because the field has become much more massive, we can't build up this extra potential. And so we get a shallower potential well around large, massive objects. And that suppresses our fifth force. I have, yeah. So this is then the modification that we get to this Yukawa potential that we've been talking about. So if we start, so this is our scalar field. And if we start from the right-hand side, things of this expression, things look familiar. We've got our exponential suppression, depending on the background mass of our scalar field. we've got a 1/r potential as we've been expecting. And here in this expression, ma is the mass of our source, and m is the coupling constant that we've been using all along. And yes, okay, I've written 2 extra factors of Ra just to complicate this. But the key difference is this lambda here. Sorry, excuse me, I'm losing my voice. And lambda is our screening factor, the suppression of our fifth force. So if lambda is 1, this is just the force law that we've been talking about, and we have all of the problems of like how do you avoid the experimental constraints. Okay, well, the only freedom you've got is basically to tune the coupling constant to be so that the fifth force is suppressed. What we have here is that if our object is large enough, whereby what that means is that if the density of our source times the radius squared is sufficiently large, then this lambda factor becomes very small. And that's saying exactly what we just talked about here, that all that's sourcing the mass, the only mass that's sourcing the external field potential is a thin shell around the surface. And that's why if you're just using sort of small isolated objects, where maybe this core region is not very large, then you can have kind of significant forces. But for large, dense objects, actually the fifth force is suppressed. So that's one way in which we can get a scalar field which hides from our experiments without needing to tune the coupling constant to be small. So the price we've paid is that we had to give it a more complicated potential. We had to have a nonlinear potential, right, rather than a mass term. This you can check this effect doesn't happen if we just have a massive scalar field here. But what we gain from doing that is this thin shell effect, whereby it's no longer the whole of the mass of the object, the source of the fifth force is just the shell near the surface. And that leads to the kind of key observational consequence of that is a violation of the equivalence principle. So just this is just to say the kinds of things that where maybe you could still try and see the effects of this scalar. So obviously the equivalence principle is the idea that large and small objects fall at the same rate. Okay, it's apparently apocryphal that Galileo threw things off the Leaning Tower of Pisa to test this, but never mind. It makes for a useful graphic. So all our experiments to date show that if we drop things and they're freely falling under gravity, a small object and a large object fall in the same way. Now, what we're saying here with our fifth force is, well, that's true. Gravity will affect my large object and my small object in the same way. But actually, my fifth force is more suppressed around larger, massive objects than it is around smaller ones. So small light particles in diffuse environments, in very low density environments, will feel a much stronger fifth force than a larger, more dense, more massive object would. And so in those environments, the smaller objects will fall faster than the larger ones. Okay. So that's why, if we've only done our experiments to date testing gravity on these large objects, why we haven't seen the effects of the fifth force, and yet they could be there if we make kind of sufficiently interestingly designed experiments or observations. And you can think about all sorts of interesting ways of looking for this effect, either in the lab or thinking about how different components of your galaxy, like maybe the stars are large, heavy objects, and the dust in your galaxy is a small, diffuse one. Maybe they fall differently in the gravitational potential well of a cluster. So that's one way that we can get kind of interesting effects in these theories. We can have a modification of gravity with our scalar field that gives us interesting effects in one regime, but not in another, and doesn't violate our all of our experimental tests. Okay, are there any questions about that before I move on?
No. Move on, I guess.
Mm-hmm.
No, I said that I don't see any questions, so you can.
Oh, sorry,
Yeah.
sorry, I misheard. Okay, so then finally, I just want to give you one more example of just a different way of doing it, just to see that, first of all, that there are, once you start allowing your theory to be nonlinear, once you start considering the different kinds of terms that you can have, there's all sorts of interesting behavior to go away and look for, which as we said yesterday is sort of part of the reason for studying these theories, even if none of them are kind of the definitive accepted solution to the cosmological constant problem, because they give us suggestions for the kinds of modifications of gravity to go and look for. But also because the example I gave you with the chameleon was sort of an example where we had a quintessence type theory. So we got an acceleration of our universe because the shape of the potential of our scalar field and the way it evolved in that scalar field. I want to give you an example here of a theory where the opposite, where the other alternative behavior that we talked about, where you have a self-accelerating universe can arise. So if you remember that, we talked about that coming about because the scalar field evolves significantly, and maybe there's one metric in our theory which has a large cosmological constant, but because of the evolution of the scalar field, you get your rescaled metric doesn't have an obviously large cosmological constant. So the example of that we're going to talk about is what's known as a cubic Galilean model. It also this arises in DGP, series of modified gravity, coming from discussions about the motion of branes in an extra dimension.
Sorry, can I just ask? Is this not? Oh, okay. So maybe you'll explain it right now, but I'm a bit concerned about these dimension 6 derivative terms, and I mean, okay, you had it in mind too. Okay.
Yeah, you're absolutely right. This should give you this should make you nervous. This higher derivative operator, because one of the things that we're so often told is that your Lagrangian should have should be such that your equations of motion end up being second order in derivatives, right? That's what we need. We certainly need second order in time derivatives to ensure that we don't get instabilities, that we don't get ghosts. And you might look at this and count this term here. This is our cubic Galilean term. You might count the number of derivatives in this term and the number of, so we've got we've got 4 derivatives in this term and 3 copies of the scalar field, and wonder how on earth we're going to end up with an equation of motion that has at most 2 time derivatives per scalar field. Now, the first thing to say is that there's a very finite set of terms. In fact, there's 4 things you can write down, of which these are the lowest 2, where that doesn't happen. There's a very kind of at first sight unexpected cancellation of those higher order derivative terms, and you do indeed end up with a second order in derivatives equation of motion. So if you just vary this Lagrangian, this is the equation of motion you get. So the variation of this term, as we would expect, gives us a box phi. The variation of this term, obviously slightly more complicated, but when you work through kind of the algebra that you get from that, this is what you get, and we get no more than 2 derivatives per term. I might come back to the fact that these are all higher order operators and how much we're worried about that at the end, if that's okay. But does that answer your question?
Yes, sure.
Yeah. Cool. So again,
yes,
oh, is there another one?
Yeah. So it's a follow-up question. So so my question is why cubic? Because the most general Lagrangian that we can write that is invariant under Galilean transformations have 5 terms in 4D, and there I only see the second and third terms. Like I'm missing the first, fourth, and fifth.
Yeah, so again, what I've chosen to do actually throughout these 2 lectures is to try and make choices to keep things as simple as possible, so that I can actually sort of try and indicate to you how the calculations go. It is absolutely true that there are other terms that we could write down here that have this same structure. So that look like they have higher order terms that do have higher order derivatives in the equation of motion. Sorry, that do have higher order derivatives in the Lagrangian, but don't give you more than 2 derivatives per field at the level of the equations of motion. From the point of view of what I want to, the point I want to make about how that affects the force laws, essentially the same kind of phenomenology occurs, which is why I've just chosen to stick with these for the moment, but I will come back to mention them in a moment, if that's okay.
Okay, so if I understood correctly, these are toy model, but if you had this sort of space-time symmetry in nature, you would have to take all terms, no?
Right. Okay, maybe let's have this discussion now. So first of all, what I haven't said, but which you're alluding to, is the fact that this Lagrangian has a symmetry, which is that it's 2 symmetries. Firstly, that the field is invariant under shifts of the field. That's kind of obvious because all we've got here is derivatives, but it's also invariant under shifts in the derivative of the field. So I'll write like that. And this is what's, no, sorry, is that? No, hang on, sorry. Oh dear, this is because I didn't plan to talk about this. Let me write that again. This is the symmetry of the series. Yeah. So there's another reason that these terms are special, not just because they give you second order equations of motion, but because they're invariant under this symmetry of the theory. And the symmetries are always good because they tell you, they give you a reason for picking a subset of operators and not others. And this is a point that I didn't make when talking about the comedian, but which absolutely is a valid criticism of this theory, which is, why on earth have you chosen this potential? And how do you know that there aren't other higher order terms, higher order operators that you should be including as well? And in the comedian model, if we were really believing that this was the fundamental kind of description of our universe, it's very hard actually to justify why you make, for example, this choice of potential and you ignore other terms. There are other choices of potential and coupling function that you can make, where you can argue that there are reasons for choosing those operators are the relevant ones, and other higher order operators are negligible, or at least are subdominant. But But again, I made this choice because it kind of makes the explanation of the phenomenology in terms of the fifth force clearer. So in that sense, in the sense of like, do we have control over the higher order operators? The Galilean models are nicer because you do have this symmetry. So you can say, well, I have a reason for keeping the terms in my theory that respect the symmetry, and anything that breaks the symmetry is going to be subdominant. And then again, you're absolutely right that I should have written down, if I wanted to think about this from an effective field theory point of view, I should have written down all of the operators that respect the symmetry. And as I said, I haven't done that because the point that I want to make about how the fifth force behaves, we can see just from keeping these first two. But yeah, you're absolutely right that they should be there, or they should be there if that is your way of constructing.
One last thing, you only have a term that is despite without derivative, without four derivatives, no?
Yes.
Why does this not appear?
So again, it doesn't appear largely for the reason that I've just said, which is that I'm sticking to the simplest version of this, which shows the physics that I want to demonstrate. Yeah, so there is, yeah, that's the only reason, basically. I'm trying to give you a simple version of the calculation. Okay. So, right, this was our equation of motion, where again, this term on the right-hand side comes from the same coupling to matter that, that we've talked about before, where this is our energy density, this is the density of our spherically symmetric source of radius r and density rho. Sorry, the page. And if we say that our situation that we're interested in is a static source, which is spherically symmetric, then our equation of motion can be written in this form. Okay, so this is just this is our box phi is this first term here, and then this term, which has come from the higher order term in our Lagrangian, gives us this term. Sorry, gives us this term here, the one that's coming in with the C3 and the 1 over lambda in front. Okay. So then what does the force look like in this picture? How does the theory behave? So I just need to scroll down my notes. So we can solve this again in the way that we have been talking about. We separate the behavior of the field into two regions, one inside and one outside the source, and then we match them at the boundary, and we say things don't diverge at the origin, things don't diverge at infinity, and that is enough information to completely determine the behavior of the scalar field. And if you go through that calculation, what you find is that outside the source, r greater than r, phi prime, I mean, you can see actually that this, if we're just solving for phi prime, actually this is just a quadratic equation. This piece is quadratic in phi prime, and we can integrate up once when the density is constant. So this is actually relatively straightforward equation to solve. And we find that we get phi prime. So I'm again skipping the steps to get there. We find this 1 plus. Sorry, I'm just going to write it out, and then we're going to talk about the behavior. Okay, we get this expression. So this then looks, so we know that our force as well, our scalar mediated force, is proportional to phi prime. So this is already an expression for our force. But we have a much sort of different behavior dependence on R to the one that we're used to, the one we've been talking about in our Yukawa yeah, in the Ikawa force that we've been returning back to. Now you can sort of see that there are going to be two regimes of behavior, depending on whether this term here is larger or smaller than 1. If it's smaller than 1, we can expand the square root in powers of this term. Then the -1 here, the leading order piece will cancel with the +1 that comes from here. And the R here will cancel with one of the factors of R here, and we'll get the 1/r² force law that we're used to. So very large distances where this term becomes smaller than 1, we do recover the standard behavior. So at large R, we find that F goes like 1/r², as we would expect. But at small r, we can see that the behavior is very different. So if this term dominates, then we're going to get a very different scaling of the force law with R. And actually what you find is that there's a characteristic radius which separates these two types of behavior, which is called the Weinstein radius, which looks like this. And when R is less than RB, what we find is that our force scales like, what does that turn out to be? We're going to get 1 goes like 1/r to the 1/2. Okay. And in fact, the ratio of our Galilean force to gravity will go like R/RV to the 3/2. So once you're inside this characteristic radius, the force is suppressed. Okay, and it gets more and more suppressed the deeper inside this Weinstein radius, this characteristic radius you get. And that's all to do in this example. It's clear that it's to do with whether this term under the square root is bigger or smaller than 1. Okay, so you can see that that's where this scale comes from this combination of stuff here. Okay, so I've only got 5 minutes left, so I really do want to wrap up at this point. So what I've tried to show you today is that sorry, excuse me, is that there are ways of getting around these constraints on the fifth force. That one of the, so it is possible to construct theories that have significant effects on cosmological scales, but that hide from our local tests. And the key to doing that is to think about nonlinear terms. Okay, so we've seen the chameleon model, and we've seen now quickly a Galileo model, and we've seen that by either modifying the potential or by modifying the kinetic structure of the theory, and adding in nonlinear terms and higher order operators, we can affect the way that our force is sourced by matter, and how we can suppress the scalar field locally, suppress the effects of the scalar field locally without having to fine tune anything, or at least without having to tune any of our coupling constants to be super small. Now, unfortunately, neither of those theories that we've talked about are perfect. The Galileo model that I've just shown you, I said it does have a self-accelerated solution. Unfortunately, that is true, but unfortunately that solution is in conflict with other cosmological observables. In particular, it gives you the wrong sign ISW effect, so it's definitely ruled out by cosmological observations. I didn't have time in these two lectures. I wanted to give you this story about how the forces are suppressed locally. So this connection between large scale cosmology and small scale kind of laboratory and solar system tests. There's a whole sort of slew of literature about how you do cosmological tests of these theories. And the kinds of cosmological observations that you would think about to also try and look for their effects on cosmological scales. And there is a link or a reference in the lecture notes to a very nice summary of what those look like if you're interested. So I'll stop there. I guess we have a few minutes if there are any final questions. But yeah, thank you very much.
I have a question.
Sure.
I have a question. So if I understood correctly, the way these models mimic the cosmological constant is because at late times the Hubble friction dominates, so the field gets stuck. But I would have expected the Hubble friction to dominate at early times because the Hubble rate was bigger at early times.
Right.
About that.
So yeah, no, that's a really good question. And actually there are two there are two types of models of quintessence actually that are called freezing and thawing, and they're exactly what you've been talking about, whether it's the large Hubble constant at early times which freezes the field, and then as the universe expands and evolves, eventually that friction term becomes subdominant and then the field starts to roll. That's a thawing model of quintessence. And then there are the ones that I've talked about where that term only becomes important at late times. And what determines which of those behaviors is the right one is just firstly the initial conditions you choose for your scalar field, how much kinetic energy it has initially, but also the choice of potential as well, whether at early times the friction term dominates. It will depend on this combination of how much kinetic energy there is, how much potential energy there is, and yeah, you can get either of those types of behavior, and you can use either of those types of behavior to give you a quintessence model. So there's a review article that I've linked to in the lecture notes by Ed Copeland and two other authors that has a really nice discussion of how that works.
Okay, thank you.
Also, so for this cubic Galilean model, if we changed frames to the Jordan frame, is that where we would see a very large cosmological constant?
Yeah, so that's the idea that, yeah, so obviously I'm working now in the Einstein frame because I've made the coupling to matter explicit, but yeah, the relationship between the two frames, it's you need a very large, as we said yesterday, you need a significant evolution in the scalar field, and then over sort of cosmological time period, and then you get two different pictures, two different frames, and two different amounts of acceleration. Yeah.
Okay, thank you.
Okay, so I don't see any further questions. Thank you very much for your lectures. Yeah. Thank you very much again. And let's hope the next time you can come in person.
Yeah, fingers crossed.
Okay.
Very nice.
Bye-bye.